So my day starts at 4 o'clock in the morning. We are in the south of France, near Marseille, and we have to bring this component 100 kilometers to the ITER site.
The
energy landscape is in flux worldwide. The reality is, demand for energy is growing.
The issue of energy has become very urgent.
In order to address the problem of this planet, we have to work faster, I think.
Fusion could be the game changer.
We urgently need safe and clean sources of energy for our planet. Is nuclear fusion the answer to the energy and climate crisis? Will scientists and engineers be able to unleash the potential of fusion before it's too late?
100 years from now, what energy are our grandchildren going to use?
Ultimately, the discoveries of our research belong to the world.
Nuclear fusion is a process that occurs naturally in the sun. Scientists want to mimic that process on Earth. Thousands have been researching just that for over 30 years. In April 2020, the first magnetic coil was delivered for ITER's experimental reactor.
We're seeing today the birth of the real big players of tomorrow.
ITER is the biggest and most complex project human beings have ever tackled.
You have the hottest place in the galaxy right here and the coldest place on Earth just a few meters away down there.
The fuel that we need can be inexhaustible.
Fusion is the most natural thing there is.
Same process as the sun.
Nuclear fusion is fundamentally different from nuclear fission, which is generating power by splitting atoms. ITER is the biggest fusion research project in the world. Here, the United States, Russia, China, Europe, and other partners are working side by side because all are convinced by the potential of fusion technology.
Behind me is the construction site of the ITER project. This is where the tokamak reactor will be located. And this is what we are trying to do in ITER. Get the physics sorted, but do it in an environment which would be utilizable in the future as a commercial source, and not something where we do an experiment, somebody gets a Nobel Prize, and then that's over. I think that's the intention of ITER, is to have a future beyond.
Researchers at the sprawling ITER complex are approaching this mammoth task using magnetic confinement fusion, or MCF. At the heart of the project is the tokamak. Once completed, this fusion machine will weigh 23,000 tons, made up of millions of parts from around the world. The donut-shaped vacuum vessel alone will weigh 8,000 tons.
Well, actually, we are now in the assembly hall of ITER. This is where a lot of activity is happening right now, and this is where we put together the 9 sectors of the vacuum vessel before they are being actually lifted into the tokamak pit and fully assembled over there.
The role of ITER is really to demonstrate both the principle and the technology and the safety aspects on a device which has the size of a reactor. After that, the industry will have the recipe, if you wish, to construct the reactor of the futures and to make that a series production.
So these 18 blocks that you see surrounding the center here, they are the supports for the toroidal or D-shaped vertical magnets that will surround the vacuum vessel. And in the end, when this is going to be removed, there will be a massive, powerful magnet on the inside. It's the central solenoid. This will be the strongest magnet ever built by mankind.
Behind us is a big vacuum vessel. This one, for example, comes from Korea. We also have vacuum vessels from Europe, from Italy. They're brought here.
And once everything is put together, we will actually have then the fusion machine in here, and this is going to be where the fusion reaction takes place.
Where I stand, there will be the vacuum vessel, okay? And attached to the vacuum vessel, you will have 440 modules of the blanket covering all the vacuum vessel and facing the plasma, and roughly about 600 meters square in area.
I predict that in 10 or 20 years, we won't be able to stand here anymore because it will be far too hot. That's because we're aiming to replicate the sun, and here right behind me is where the vacuum vessel will be. And these vacuum vessels are the central component of the whole fusion process.
We are speaking about 20 billion plus. It's the order of magnitude, and it's likely to go a little bit north of that, if I may say, or south of that, depends on the way you see it. The cost of the last World Cup in the Middle East was between 100 and 200 billion. So I think that we have two things, put things in context. Here on site, we have about 5,000 people. We have 7 members, and of course in Europe, you know how many European countries there are, but Europe come as one. I think that here we leave the passport at the entrance. And indeed, there are some Ukrainians that actually came originally through the Russian Federation, because Ukraine is not per se a contributor to ITER. It's quite remarkable. I think that in ITER there is still a consensus and focus of all these members to try to get this project realized together and try to solve, at least contribute to the solution.
We are in the cryostat workshop here at ITER on the work site, and what's coming into sight right now is actually the last piece of the cryostat itself that we are putting together here. Basically a giant thermos. The reason for that is that it will create an environment that protects the vacuum inside and the cool temperatures. What's happening right now here, it's the cover of the cryostat that's being built here that you see up top there. It's basically just the top lid. It's 3,800 tons altogether, all 4 sections together. And as you can see by the size, it's 30 meters across, it will be 30 meters high. You just can't transport that easily. So all the parts have actually come from India, have been welded here together into the 4 sections.
Fusion is certainly a technology which is very, very complex. And so how this will be deployed is a question mark.
The principle of fusion is that we want to take light particles and smash them against each other as hard as we can. And when we do that, they will fuse, hence the word, and part of their mass will transform into energy.
Energy and mass are ultimately interchangeable. You can transform mass into energy and energy into mass. It works in both directions. There's a famous formula, E equals mc squared. Everyone knows it.
The energy we can harvest, we can pick it up to then power our houses, our industries, our systems in society.
What we need to get this actual fusion reaction to happen is we need our 2 initial reactants to get close enough that they will actually fuse into our final product. Unfortunately, this is fairly difficult, and the main reason for that is that our 2 initial reactants are both positively charged. And in the same way that 2 positive ends of a magnet will repel each other, so will they.
So fusion for me, it's a bit complicated process, like when you try to bring 2 similar people together in society, it always gets complicated. And likewise, when you have 2 small positively charged particles, when you try to bring them together, it's always get complicated. So for example, when you have 2 hydrogen isotopes, one deuterium, one tritium, both being positively charged, when you try to bring them together, they repel because of the electrostatic forces being involved. But if you energize them enough that they can overcome this barrier, then they come together and they fuse. When they fuse, a lot of fusion energy is being created. Of course, during this process, a high energy neutron is being ejected, and alpha particle, which is commonly known as helium, is being created. And this fusion energy can then be converted into electricity, this low carbon energy, no carbon electricity, which is good for the future.
Fusion happens in the sun's core in extreme conditions. It's extremely hot and very dense. That's one reason why the sun or some random star can't be simply transplanted to Earth, because it only works in space, so our approach has to be a bit different.
The sun is very big, like all the stars, and gravity makes all the mass of the sun stick together. Now, we can't quite make a star that big into our laboratory, so we have to come up with something smarter.
So even when we say we use solar energy, we're actually going to use the energy coming out of fusion reaction and recreate these conditions, or try to recreate similar conditions than those that are taking place in the sun. We just try to take a shortcut here.
One way is plasma confinement in a tokamak. Inside the reactor, the donut-shaped vacuum vessel is surrounded by electromagnets. A tiny amount of hydrogen injected into the vacuum is plenty.
And then you switch on a solenoid which is in the middle of the tokamak. And this, by the magic of physics, creates an electric field in this donut.
The hydrogen isotopes deuterium and tritium begin to swirl around in the vacuum. An initial heating system converts the gas into a plasma. Further heating processes using electromagnetic waves and neutral particle injection are required in order to heat the plasma to temperatures of 150 million degrees Celsius.
And then the process of fusion starts. The particle can knock each other sufficiently fast so they fuse, and then they produce energy. Then you have lit a sun inside your cage.
Now neutrons are neutrally charged, so they're no longer captured by our magnets, and they fly off and hit the wall. And in a reactor, what you would do is you'd have what's called a blanket on the wall, and as the neutron slows down in the blanket, it heats the metal. So all you do then is pass water through the hot metal, that water turns into steam, and then you take that steam, turn turbines, and produce electricity, just like turbines do in current power stations.
We look at magnetic confinement as the only process that has really survived the Darwinian evolution of fusion systems over 60 years and more of fusion research.
There's also another type which is called inertial confinement, which requires you to just get very, very high densities and temperatures for a short period of time. Most commonly this is done with lasers, but there are other approaches using more sort of pneumatic, just straight up physical methods to compress something.
A tokamak and accelerator are similar in that they're both magnetic confinement bottles. Tokamaks have emerged as the most conventional way of trying to confine plasmas, and they have reached marvelous results. The cousin of the tokamak is the stellarator, which actually was invented before the tokamaks, but it was so complex in its design and then in its construction that it remained as a little cousin, so to say.
Once finished, the ITER tokamak fusion reactor will be the largest of its kind worldwide. Meanwhile, the world's biggest stellarator fusion device is located in northern Germany. The project is called Wendelstein 7X.
Wendelstein is a mountain and hiking trail in Bavaria. The paths wind up the mountain in a way that's reminiscent of the shape of the magnets that we have in this machine. So that's one reason. And secondly, because the oldest stellarator, the first stellarator to actually get up and running, was in the mid-1950s at Princeton. The project director, Lyman Spitzer, was a famous astrophysicist and an avid mountain climber. And he called the research work Project Matterhorn. And then Werner Heisenberg saw it and said, then we'll name our project after a mountain too. So this project is called Wendelstein. The Stellarator project in Germany has the name of this Bavarian mountain, but it's located in Pomerania. Not as a mountain, of course, but as a machine. The Wendelstein 7X Stellarator. It's a major fusion research facility and located here at the Max Planck Institute in Greifswald.
The Max Planck Society decided to show its muscles when it had the first large-scale clusters and had the knowledge and the know-how to then go and optimize these Stellarator devices.
We have 450 employees here at the Institute. Roughly half are technical and engineering staff, and the other half are physicists and computer experts. This is the Torus Hall, the Wendelstein 7X, there you have it. This building went up in 2000. This hall was empty back then, nothing in it. The first components arrived in 2005, and then assembly of the machine got underway. The total cost of everything put together was 1.3 billion. The investment costs for the machine standing here were around 400 million. Actually, the stellarator and what's known as the tokamak, the other concept which uses magnets, are almost the same. Both are ring-shaped magnetic fields, but there's a difference. In a tokamak, there's a very strong electrical current, and this current also produces part of the required magnetic field. That's not the case with the stellarator. In other words, in a stellarator, there's not a strong current in the gas, in the plasma, and that makes the plasma lighter. As a result, it's more stable because, in truth, it really doesn't want to carry any electric current. It tries to ward it off with everything it has, with both hands and feet, so to speak. It doesn't have hands and feet, of course, but it fights it with an unstable reaction to this electrical current. And that's why it's good to get rid of this current. It solves a whole lot of problems. Because there's no electrical current flowing in the stellarator, the magnetic field must be configured. That's a requirement of physics. So it hinges on how it's shaped, and that's where all the research is focused. Decades of physics research has been devoted to the shape of this magnetic field. The shape of the magnets can determine the shape of the magnetic field. It's the most accurate shape of the magnetic field that you can imagine, even if it looks very odd. We essentially asked nature how the magnetic field should look, and this is the answer. Wendelstein is far too small to produce electricity. It's scaled down as much as possible so we can still learn from it to determine what works. We're researching so that we can achieve the state of matter in this magnetic field. So that if we were to put fusion fuel into it, we would get fusion. That's what we're finding out. That's the mission. Here they're setting up an access point to climb into the machine. Work is starting again on the interior of the vessel. Our technicians and engineers will climb in there, the physicists too, and they'll be working inside the machine.
I'm amazed that we made it. It was so difficult. And it's a good machine. It's working really fine. It's fun to work with this machine. It's so tame, it's so cooperative, because each machine has a soul. I must say the machine has a good soul. Sometimes if it was a hard day or a frustrating day, then it's always curing to go here and just to have a look, and then you know why you're doing it. It's a beauty in its own, yeah. So people say, so this is a kind of pinnacle, or at least a very nice example of German engineering. Looks so German, because everything is shiny and tidy. It's science cast in steel.
The first fusion companies emerged in the US and Britain, but Germany has really caught up in recent years, and it really has a terrific foundation. The Max Planck Institute for Plasma Physics in Munich operates two of the biggest fusion devices in the world, namely Aztec's Upgrade and Wendelstein 7X. Germany has long had the scientific know-how.
If you compare, for example, France with Germany, the amount of carbon dioxide produced per capita in France is half of the one produced in Germany, notwithstanding the fact that in Germany there has been a tremendous amount of investment for renewable energy. Still, it's about half. I think Germany is a prime candidate for nuclear power. I'm sorry that to some extent I've been living there for quite some time. There is good quality, good technology, and I think in general nuclear power would be well placed in Germany. And fusion is one of the possible sources, is of course for the long term.
In Germany, when you just mention the word nuclear, people immediately react as though they're a bit allergic to it. That's why a great deal of educational work is needed, so that people understand the differences. In one case, a large atom is split. That's fission, or atom splitting. In our case, lighter atoms fuse together.
Fusion is a nuclear technology as well, so you have to address the topic of protection from radiation. You need rules, you need regulations, you need the procedures to handle it.
Regulation cannot be overestimated in its importance. If regulation were not to be right, we would have to design power plants for the wrong requirements. We would have to overcomplicate the system and make it even more complex than it already is. And this is not to anyone's advantage. It's certainly a challenge to develop an industry where regulation itself is being created. We have regulation related to power plants of all different sorts. We have the threat in fusion to be mixed up with fission, the other kind of nuclear, which is about splitting uranium. Fusion has relatively little to do with the other nuclear, but in people's minds, the two seem quite similar. So there is a real threat to social acceptance of this new technology. If we don't regulate fusion in the right way, we could make more damage for the history of humanity than we may realize in practice.
So in this vacuum vessel, toroid, we will generate vacuum and then plasmas and then heat them up, or we bring them up to a really high temperature of 150 million degrees Celsius, which is 10 times more than the core temperature of the sun. So now we have got two things, vacuum, then plasma, which means high temperature. Now you need to contain this in a dense form.
This we can do. We can do very high temperatures, we can do very high densities, and we can confine these hot matter, these plasmas, for a long time. But can we do the things at the same time? At 100 million degrees, some marvelous things happen. You start having particles colliding so often at such energy that you get the statistical conditions where enough fusion reactions are happening to overcome the level of expenses that you have in heating the system in the first place.
A plasma is the fourth state of matter from the basic ones, where you start with a solid, add a little bit of energy, you get a liquid, add a bit more energy, you get a gas, and then if you add even more energy to that, you end up with a plasma. And a fun one with plasma means that your whole gas becomes charged, and that means you can hold it in place with magnetic fields, but there are a number of different other approaches. Most of those still rely on what we call magnetic confinement, which is keeping the plasma confined by using magnetic fields.
Yeah, so without magnet doesn't work. And the essential thing about magnets and magnetic field is that we have to get this plasma hot, and 150 million degrees for something that weighs a few grams. The process is called magnetic confinement because we want to basically make sure that the plasma is detached from the wall and compressed by a magnetic field. So there must be a current in the plasma, and there must be a magnetic field. This magnetic field is generated by the magnet itself and basically allows the plasma to be separated from the wall. It's a bit like, when you see magnetic levitation and you see that an object is being able to float on a magnetic field.
A pioneer among large fusion reactors is located in Britain, the Joint European Torus, JET for short. Since it came into operation in 1983, experiments using JET have resulted in a number of fusion breakthroughs. These insights have been woven into the development of ITER.
This is JET, which is the biggest operating tokamak in the world currently. This is the JET in-vessel training facility. The actual JET experiment is through a big thick wall over there. JET is the largest operating fusion experiment in the world. We don't put power on the grid. It's an experiment run by Eurofusion. You can see it's kind of got a circular shape. It's quite hard to see from this angle, but it's a donut shape, at least on the inside, and that's key for fusion. So if we were in the real JET tokamak, well, the vacuum vessel would look much as you sort of see. So where this robot is, here you'd have about 150 million degrees, which is what you need for the fusion reaction. And then just under my feet, under here, you have special pumps that are at 4 degrees above absolute zero. So you have the hottest place in the galaxy right here, and the coldest place on Earth just a few meters away down there.
Even though projects like JET have been around for decades and the principle of fusion was proven in the mid-20th century, the technology is still not ready for prime time. Hence the old joke that fusion energy is always 30 years away. Even still, more and more private investors believe in the potential economic success of fusion.
Ja, die Start-up-Szene, die ist sehr, sehr breit.
The startup scene is really broad. More than 50 companies have been set up worldwide. Proxima Fusion is one special example for us, because the founders of this startup are young people from our institute.
Proxima Fusion is a spin-out of the Max Planck Institute for Plasma Physics. We are based in Munich, and we're working on quasi-isodynamic stellarators as a way to make fusion energy. The mission of Proxima Fusion is nothing but putting energy on the grid. This is an incredibly large objective, of course. Our public institutions have been doing research on the topic for decades. We've now built such know-how. It's clearly time to transition the field, to complement it with more and more engineering. So Proxima is working to think about the many engineering systems that are needed to actually convert something from a scientific project to an energy-focused project. We must be humbled by the really standing on the shoulders of giants, and we need to make the most of the opportunity of translating this research into a new industry. So the interaction that Proxima Fusion has with the Max Planck is based on collaboration agreements.
There's a transfer of knowledge taking place, because ultimately the discoveries of our research belong to the world. We're funded by taxpayers, so as a result, all that we uncover belongs to humanity, startups as well.
We are trying to build this relationship in a complementary way. There are things that are not within the Max Planck's mission. Commercialization is not one of those. Engineering at large scales towards energy-producing systems are not within the Max Planck's mission, but they're very much within what we need to do. I think it's very natural for W7X's transition to lead to the next step of the story. We can develop this technology that we're working on and make this a source of energy that lasts effectively forever for humanity. These power plants that we're thinking of, they could be placed anywhere in the world. The dream would be to have a stellarator power plant in every big city in the world. We are not trying to build the electrical connection to the grid. We need to understand it in order to be able to address what are the needs of that system. We want to sell stellarators rather than energy itself. So as we go and develop these designs of power plants, the question of what is the cost per kilowatt, per megawatt that you are able to deliver, that is the key question. W7X, to our eyes, is the kind of device that shows the clearest and most robust way to fusion energy. The advantage, though, of dealing with the complexity of a stellarator over the simplicity of a tokamak is that a tokamak has operational issues, so to say. It's very difficult to actually run it. It's definitely an exciting time in terms of how much is happening in the private fusion industry, and I find particularly exciting the interface between the new private industry and the public institutions. It's that interaction, I think, that can speed us up.
The issue of energy has become very urgent, and it's really starting to hurt in terms of energy supply and the impact on the environment and climate. So these initiatives are gaining momentum.
Gauss ist ein europäisches Unternehmen.
Gauss is a European company. The companies that founded Gauss Fusion have been working in fusion for decades. In 2022, they had the idea to merge and set up Gauss Fusion in order to build a first-of-its-kind fusion power plant. We're different from other companies in this sector because they're largely spin-offs from universities or research institutes. Gauss is the new kid on the block when it comes to fusion.
Some of them are trying to utilize some existing technology, maybe with very ambitious goals. Some of them are trying to introduce new ideas. Some of them are trying to develop some specific technologies, for example, magnet technologies. There is a very, very large variety of ideas that are broiling in, say, in startups around the world about fusion.
ITER ist das größte.
In my opinion, ITER is the biggest and most complex project human beings have ever tackled. ITER is doing truly pioneering work. We wouldn't be here talking about fusion if it weren't for ITER. It's taught us a great deal and will continue learning from ITER in the future. It's essential that we implement what science has shown us. And this implementation can only happen through industry. Now is the time where industry steps in and builds on everything we've learned from science. Both the tokamak and the stellarator have advantages and disadvantages. The geometry of the stellarator is very complicated compared to the tokamak. But stellarators are better than tokamaks at using atoms to control plasma. So both have pros and cons, and both present their own challenges. And we're investigating which one we'd like to work with in the future. Every new technology needs some kind of seed money. Think of how solar and wind energy began. Without initial support from the state, these renewable energies wouldn't have been able to make the important contribution they're making today.
If you look at the future, how we're going to power our society that keeps growing in size, in consumption, we will need more and more energy that is baseload, that goes and complements the renewables that we love and know so much. The wind, the solar, we need something that is not intermittent. There are a number of technologies that are developing, will keep developing. They're great. We should keep pushing on those, but we shouldn't make ever one bet. We cannot have a single point of failure in the development of society.
Renewable energies are truly a wonderful thing. But they have a problem. They're intermittent, meaning they're not always available. If the wind isn't blowing or the sun isn't shining, there's no electricity. And either you store it, and storing is very, very difficult when you're talking about these huge amounts of energy, or you fill the gaps and compensate using another source.
Look, I think I don't need to expand on the importance of reducing significantly our dependency on fossil fuels. As of today, notwithstanding the targets that have been set by many governments, collectively in the world, we keep increasing carbon dioxide production, and it's still going, in the wrong direction. And when you look even at countries in the Western world which have implemented major, steps to reduce, still it's not going down fast enough. So we have to find a solution.
When it comes to financing, the time frame makes things tricky. We're talking about projects that span 15 to 20 years, so funding them becomes somewhat complicated. The return on investment won't come tomorrow, or in 3 or 5 years' time, which is what conventional private equity companies are accustomed to.
I think fusion as a commercial bet, as an investment bet, it's a difficult one. Objectively, it's very difficult for an investor to understand the entire landscape. And identifying those companies for an investor, distinguishing between the different physics and engineering concepts can be extremely challenging. The size of the market that we're addressing with fusion power plants is enormous. So we're seeing today the birth of the real big players of tomorrow.
The fusion process is already 1,000,000 times more efficient than the process of combustion. For a large coal-fired power plant, you need tens of thousands of tons of coal a day. That's 2 shiploads. And for a fusion power plant with a similar capacity, you just need a kilo. That's about a bucket. That means, in the morning, a staff member can bring the fuel in a small bucket. That's just astounding.
Fusion uses as a fuel, in the way we look at it, heavy forms of hydrogen. These forms of hydrogen can be created, partly widely available in seawater, partly we can create them in a self-sufficient way, produce them within our own power plants.
As the neutron slows down, if you put lithium in the blanket, the neutron hits the lithium and breeds tritium. It creates its own fuel, and so we take the fuel that we've made in the blanket and recycle that and put it back into the reactor.
This means that the fuel that we need can be inexhaustible. By inexhaustible, I don't mean that it's easy. I mean that we can develop this technology that we're working on and make this a source of energy that lasts effectively forever.
It's just an amazingly efficient fuel, and it's readily available. It's not like you have to be on good terms with someone who has this fuel and then pay them loads of money. In principle, everyone has it.
Fusion
comes with many challenges. One hurdle it needs to overcome is public acceptance. It's a new technology. People don't know what fusion is, so there has to be a lot of educational work done, among other things.
Despite being a nuclear technology, fusion doesn't have the major problems typically associated with it. Two in particular. One is the loss of control when a power plant breaks down, which we've unfortunately experienced a few times already. That's brought on by either external or internal factors. In principle, that's not possible with fusion. That's because this hot, thin gas, which has to be built up, collapses as soon as something goes wrong. It goes out by itself. The second point is the permanent storage of highly radioactive material. Fusion doesn't produce material that remains radioactive for a very, very long time, 50,000 to 100,000 years, so we don't need final storage.
In the 1980s, everybody realized at the time that to get fusion, that would entail complexity associated with size. And this was the time when the Gorbachev and Reagan, they found this as a potential area of cooperation.
The global cooperation at ITER continues. Many are hopeful that, unlike fission, nuclear fusion could be the answer to our endless appetite for energy worldwide. But critics question if the process of fusion is really as efficient and clean as it's touted to be. While the principle of fusion may be relatively simple, the technical challenges are so great that researchers are constantly having to solve new problems.
The material is one of the biggest challenges because of high temperature, because of low temperature, because of high magnetic field, because of high neutron flux, and all of it together within a couple of meters. So we have created new materials for fusion.
Aside from the technical hurdles, there are other challenges we need to address. Labor, for example. We need a lot of people with specialist knowledge in the future to build hundreds of fusion power plants.
There are just a few steps missing, and then we should be able to get it off the ground, despite the major technical challenges. Because ultimately, all of the limitations are technical in nature. There's nothing in physics to speak against it.
In principle, nuclear fusion is a source of energy that's CO2 emission-free. But is it really achievable on a large scale? And will it be ready in time to avert the worst effects of climate change?
Fusion works, there's no doubt about it. There's no need to further prove that. It works and people know that. Fusion on Earth is a bit more complicated, but now we've come so far that we can just about smell it. We're getting really close.
One cannot overestimate the importance of some form of naive optimism. You know, that the hope, what we're trying to do is so ambitious, and there will be so many challenges ahead of us. But the objective, the mission that we're after, is so great.
Fusion research is so challenging that we have to keep passing it from one generation to the next. We're in the third generation now.
ITER is really, at the core, is a scientific experiment. I think it's before a prototype. Prototype is already something, in general, in engineering, it's something that you know, you want to test whether it will just work for the intended purpose. So a prototype for a fusion reactor should produce power. This is not what ITER will do. It is a scientific experiment which has been sized and dimensioned in such a way that if it will be successful, it will allow to proceed. And the idea in the fusion program is a similar type of reactor would be built based on the knowledge developed by ITER, and that maybe will eventually yield to a prototype. So we are a little bit far from a prototype.
There are a number of things that need to be part of this cocktail of ways of addressing climate change. Fusion is a big beast in there. It could do so much. If we get fusion going, humanity will be different. We enter a new era of human civilization. That's enough said.
We have to work more, say, in a more expedite way in order to address the problem of this planet. We have to work faster, I think. As I've seen very often, that people think, okay, let's wait for fusion and fusion will solve all the problem. I think this is not responsible from my standpoint. This is not a message I'd like to convey to you. So we are in the process of redefining a new baseline, and this is a new schedule. We have to get it right.
We're planning to finish a first fusion power plant by the early 2040s.
We do not currently have any single technology or even mix of technologies that we can say will definitely provide sufficient energy for a growing population and a growing standard of living ad infinitum. And if we were to be able to make fusion a reality, that may well be true, that we could have that security.
Fusion will be the energy of the future, but whether it would be right for the energy transition, that's for us to answer. The objective of all the fusion companies as of now must be to develop fusion energy to connect our models, our prototypes to the grid within 20 years.
Fusion is a reliable, inexhaustible, and clean source of energy that harms neither the environment nor the climate. And fusion offers benefits beyond that. It gives us energy independence. That means it makes us independent of global international supply chains.
Now is the time when we're entering the field, translating research into an industry that can then scale to meet our climate challenges. The speed is the key aspect of all of this. The question is not whether we will get fusion, the question is just when at this point.
First of all, we need energy. Second, we need more energy for the developing world. Third, we need energy that doesn't emit any CO2 into the atmosphere. And fourth, we need energy that's safe and available to everyone on Earth.